Alright, so do you have any question, guys? Is there any question, any issue? Please speak up, because this time what happened, if you do not talk or if you do not respond, then it would be difficult for me actually to trace you whether you are getting my point or not. So that's why definitely I need your response to make this class successful. Otherwise, it would be simply that useless. And remember, this chapter is very important for your meet. You will get one question from these topics, Newton's law, with and without friction actually. So that's why it is very important topics we are going to talk about right now. But I wonder, where is my class representative? Where is she? All right. So can you see my screen?
Yes, sir.
Yes, sir.
All right. So what is the last topic I discussed in your class? The last day, probably I start talk about that free body diagram, and then I also solve a problem which is 2 and 3 kg body stick together. We apply the 10 Newton force, right?
Yes, sir.
That was that last topic I discussed in your class. All right, let's start. Let's say I have a object which is on a surface. It's a frictionless surface. Remember, we're going to talk about this one, which has a mass m, and I'm going to drag the system with apply a force F, which makes an angle theta over here. Now I want to find out what should be is due to that force it's moved towards that direction with the acceleration a. I want to find out what would be its acceleration. And I want to also find out that a normal reaction force provided by the surface, what should be that? Alright, so if I want to draw the free body diagram, then I need to know how many forces actually acting over here. Can anyone tell me how many forces are acting over there? How many forces are?
So there are three forces acting.
There are 3 forces acting over here. That's good, very good. What are they?
So the weight, the normal reaction force, and the external force.
Exactly. So this is actually that weight. This is that normal reaction force, which is to be towards that upward, which is perpendicular to that surface, and this is my applied force, which is the external force actually we say. That's good. Now if I say this block is moving for this applied force, that should be a little bit technically wrong actually, because if it is, then this block supposed to be moved into that direction, right? But it's not moving towards that direction, it is moving towards that horizontal direction. If I draw this reference axis, which is x and y axis over here, it will moving actually along the x direction, right? So that's why I can say there will be a component of force F towards that direction, which we can find out, which would be F cos theta, right? Because this is the vector F, which makes the angle the theta, so that's why its component should be F cos theta. And one more component, it should be F sin theta, that should be towards the upward direction. Am I right? Do you understand this free body diagram?
Yes, sir.
Fine. So if it is so, then first of all I can write the net force along to the y direction over here is going to be the 0, right? Because that block is not moving along to the y direction at all over here. it is only moving towards the x direction. So that's why the net force along to the y direction would be 0. Now if you look at these, the forces along to the y direction, there are three forces. One is actually n towards the positive y direction, one is f sine theta, which is a component of f, that is towards the positive y direction, and another is mg, which is towards the negative y direction. Then I am supposed to write it should be n plus f sine theta minus mg equal to the 0. This is the forces. N is towards the positive y direction, that's why is the positive sign, and f sine theta is also towards the positive y direction, so that's why I also use the positive sign. But mg is towards the negative y direction, so that's why I'm writing down the minus sign over there. Then I can write down this n should be simply over here, it should be mg minus f sine theta, right? That this would be actually that normal reaction force is going to be provided by the surface, which is actually different from your actual weight. Remember, actual weight, we say that actual weight we write, which is W equal to that mg, but this is actually it's called the apparent weight. It's called that apparent weight. Remember this keyword. I randomly asked you to find out the apparent weight of the system. Apparent weight is that weight which is different from your actual weight. It could be higher than your actual weight, sometimes it could be lower than actual weight. If it is different from that actual weight, that is known as apparent weight. Alright, so this is would be that normal reaction force provided by the surface, which I am going to tell you actually the apparent weight. Now what about the forces along the x direction? Along to the x direction, I am supposed to write it should be ma, because it is moving towards that direction, right? So that's why I am writing. Now if you look at this free body diagram, along to the x direction, I have only one force, which is this one, which is f cosine theta. So then I am supposed to write it should be f cosine theta must be equal to ma, or I can write down f simply from there. It should be f cosine theta divided by m. That should be that acceleration. And since it's a vector, obviously we should write this vector in term of it should be f cos theta divided by m into I hat, because that is the acceleration direction. It is moving towards that positive x direction according to my this frame of reference I give you over here. Alright, this would be actually that case if you drag a system with the applied force F, you will find out that should be the normal reaction force, and this would be actually that acceleration of the system. Alright, what will happen, let's say instead of dragging, if I push the same block with the same force, with the making and a same angle. Let's say this is my block right now. It has the mass is exactly the m, and right now I, instead of dragging, I push that block with a force F, exactly the same force, and which also makes an angle the theta over here. Fine. To find out those thing actually, same thing, same two parameter actually I'm going to calculate it. One is the acceleration, another actually the normal reaction force I'm going to calculate over here. What do you think? Which parameter will be changed over here, or both the parameter will be remain same? Can anyone tell me? Instead of dragging a block, if I push that block with the same force making a same angle of the same object, whatever I calculated in the previous case, acceleration and the normal reaction force, right now which parameter will be changed? or both the parameter will be remain same?
Sir, I think the apparent weight will be increased.
Apparent weight will be increased, all right, and the acceleration will be remain same. That's your point.
No, sir, I think the acceleration will be decreased.
Acceleration will be decreased, all right. Is there any other opinion? Thank you. It's a very good opinion, I think. At least you are talking. What about others? All right, let's draw the free body diagram over here. We have simply the three force again, look like the previous case. I'll draw, this would be my mg, is the downward. This would be my normal reaction force. Now, to draw these forces, I need to extend this force in that direction. This would be my direction of the force. Then I'll find out one component of this force would be towards that direction, right? And another force would be towards that direction. This angle is theta, then I can say also this angle would be also theta. Can I say that one?
Yes, sir.
Then this should be f cosine theta, and this should be f sine theta, right? Am I right? Do you understand the free body diagram? This is very important. Come on, guys, I'm telling you. In this chapter, free body diagram is very important. If you can understand the free body diagram, then the 50% of your problem is going to be solved. If you cannot understand the free body diagram, you cannot solve the problem from here. All right, so this is my free body diagram for when I'm pushing the block instead of dragging. Now, again, this one moving towards that positive x direction. This is my reference frame. Then I can write the net force along to the y direction would be equal to the 0, right? Why it is 0? Because again, it's not moving along to the y direction, so that's why it is equal to the 0. Then from this free body diagram, I am supposed to write it should be n minus mg minus f sine theta equal to the 0, right? Then n should be mg plus f sine theta, right? Which is actually your apparent weight right now actually greater than your actual weight. In previous case, when you actually that dragging the system, apparent weight was mg minus f sine theta. Right now, your apparent weight is mg plus f sine theta, which means this time your apparent weight is higher, right? It means that that's why sometimes it's telling you that remember when you actually your trolley bag you are dragging instead of pushing, right? You drag that one by that way because of this higher normal reaction force. If you push that system, then your normal reaction force would be higher. If the normal reaction force is higher, then the frictional force would be higher. In that case, you need more energy to drag the system. That's why sometimes it's said that you have probably that statement long in the case of long lateral, right? It is easier for you to dragging that system instead of pushing, because if you push that system, then this normal reaction force is high. If the normal reaction force is high, then your frictional force is going to be the high. In that case, it would be harder for you to drag the system. That's why you say that it is easier to drag the system instead of pushing with the same force. That's why you drag your trolley bag instead of pushing. Fine. So what about that acceleration? Acceleration will be remain same because there is only one force is from this diagram. You can see that along to the x direction. Again, I have only this force, which is f cosine theta. Then I am supposed to write it should be f cosine theta must be equal to ma, or A would be simply f cosine theta divided by m. So that's why the acceleration will be remain same in this case. The acceleration is not going to change at all. Is that okay? Fine.
Sir,
Yep.
does the change in apparent weight mean it will be easier or harder for me while pulling or pushing it?
Yeah. So because if apparent weight is high, then your frictional force would be high. So because that frictional force, if this surface has a friction, what happen actually, if you push that way in that direction, you try to move in that direction, the frictional force would be in the opposite direction, right? So and the frictional force actually define whatever Fk or Fs, it's simply that coefficient of kinetic friction into mu n, mu k into n. This is actually your normal reaction force which you can provide by the surface. If n is high, then the frictional force will be high. If the frictional force is high, then you need more energy or more force to move the system towards the forward direction. Then it would be harder for you. If n is low, right, then the frictional force would be low. If the frictional force is low, then it would be easier for you to do the work.
Sir, I get it. Thank you.
Where is my CR? The CR is present in the class today? No. CR is not present into the class, which is not fair. Alright, so let's move forward. Let's say I have two blocks right now. And I'm going to drag these two blocks by applying a force, but they are connected by the two massless string. Remember, these string are massless. There is a reason I'm telling you, because this is most idle string actually. If the string has a mass, then the system is going to be that different actually. It's not a part of this Newtonian mechanics. That could be part of the classical mechanics actually, because we are not going to consider that part. In that case, it would be difficult for you actually. So let's say this is actually that 3 kg object, this is actually 2 kg object. I'm going to drag that system with the 10 Newton force towards that direction, positive direction, and I want to find out what should be that acceleration of the system, and I also want to find out individual forces acting on these two objects. Remember, I did the same type of problem in the yesterday class. In that case, they are actually connected to each other on a surface, right? I apply a force over here, which is the 10 Newton. This is actually probably the 2 kg, and this is the 3 kg. In that case, I'm pushing. Right now, I'm dragging the system actually with the same force. And remember, I find out probably that acceleration actually that 2 meter per second square, and also the individual forces I find out for 3 kg it was the 6 Newton, and 2 kg it was the 4 Newton, right? So let's check that. Right now I rearranged them. I connected them by a two massless string, and I'm going to drag that by applying the 10 Newton force. Now I am to also find out what should be that acceleration of the system, and also that individual forces acting on this 3 kg body and the 2 kg body. Alright, so there is a point over here. This massless string has the same force on the both two sides. If you have a mass, because when you're going to drag, there will be some force. Let's say this will be the forces over here, one force, and other force would be other side, right? Do you understand? When you dragging this string from the both two sides, then there will be one force on other side, and there will be one force on the other side of the string. right? It's a conception, general conception actually. Obviously, when you're going to drag this string or stretching this string, there will be some force at the end of these two string, end of this side of this string actually. If it is a massless, then these two force is going to be the same. Then in that case, instead of saying that force, we say that this is called actually the tension of the string. That's called actually the tension. Otherwise, if the force is not going to equal, you will find out some net force, and divided by force divided by net force divided by massless, then its acceleration of this system is going to be infinite, right? Because if you, let's say, if F1 is not equal to F2, then you will find out some net force, which is would be F1 till F2. I do not know actually which one actually that higher, so that's why I write down F till F2. It means that if F1 is greater than, I'll subtract F1 minus F2. If F2 is greater than, I'll write F2 minus F1. That's called actually till sign. Then you will find out some net force, and net force divided by 0, that is acceleration is going to be simply that meaningless actually, infinitely defined actually. That's why we say that massless string has an equal force on the both two sides. In that case, we say, instead of saying that force is called actually the tension. Remember, if the string is same, then the tension will be same. If the string is different, then the tension is going to be different. This is a very important point. I will repeat again. If the string is same, then the tension is same. If the string is different, then the tension will be different. Alright, now let's draw the free body diagram. This one I am going to draw. How many force would be acting for this 3 kg body?
So there will be 3 forces if there is no friction.
Yeah, oh, absolutely. You're absolutely right. There will be 3 forces. One, it should be that mass. Let's write down is say m3 into g. I write down the 3 because of this belong to that 3 kg body. It should be n3. That's the reaction force on the block provided by the surface m3, which should be upward. And there will be one more force actually, the tension over here, right? This is the tension applied by the 2 kg body on 3 kg body, because when you are dragging this one, this 2 kg will move towards that direction. In that case, this 2 kg body will also drag this 3 kg body by applying this force T. If this apply the T, then the 3 kg body also apply a same amount of force in the opposite direction, which is actually the T over here. And these two forces are equal, right, but in the opposite direction for the Newton's third law. Then this would be one more force over here. It should be m2g. This would be n2, right? This is actually the free body diagram of this object. Alright, so I'm not concerned about basically in the vertical direction, because I want to only find out that net acceleration of the system and also that individual forces acting on these two blocks. I know, so let's write down for 2 kg body, I can write net force along to the y direction would be equal to the 0. Can I write this one? Who's knocking me right now? Sifat. So why it is 0? Because it's not moving along to the vertical direction or positive y direction. It is actually moving towards the x direction. So that's why for the 2 kg body, I'm supposed to write it should be 10 minus t equal to that 2a. And also, I'm sorry, it's a y direction. I'm sorry, it's not towards the y direction. So along the y direction, I have the two force. One is basically n2, another is the m2g. So it should be in that case n2 minus m2g equal to that 0, or n2 would be simply m2g, right? Which is simply that actual weight of the block. Now along to the x direction, you can write on the net force along the x direction should be ma. There are two forces. One is the 10 minus t equal to that 2a. Let's say this is equation number 1 for the 2 kg body. For 3 kg body, again I will write the net force along the y direction would be equal to the 0. Along to the y direction, if you look at, there are two forces. One is m3, another is m3g. So I will subtract this one because they are anti-parallel vector. m3 minus m3g equal to the 0, or I can write m3 would be simply m3g, which is again that actual weight of the system, m3g. This is that actual weight of the system. And along to the x direction, you are supposed to write along to the x direction, it should be ma. If you look at this free body diagram, along to the x direction, I have only one force, which is the t over here, right? So then I'm supposed to write it should be t minus t equal to 3a. Let's say this is equation number 2. I'm going to add these two equation 1 and 2. If I add 1 plus 2, one is 10 minus t equal to that 2a, another t actually that 3a. If you add, this t will be cancelled out.
Sir, could you please go above?
Sorry?
Could you please go a bit upwards?
Yeah. Why? You are taking the note.
Yeah, done, sir.
Alright, so then we can find out this thing would be, A would be simply 2 meter per second square. You don't have to take the note actually. I'll give you this soft copy. Just try to understand. Just try to understand that idea actually I'm applying over here. I'll give this soft copy of this handout. Alright. And I'll also post this video in the YouTube. You can access those parts from there. And that should be the acceleration of this system will move at a acceleration 2 meter per second square. Both two block actually will be moved. So that's the acceleration. And if you want to write down in terms of vector, obviously it's a vector. It should be 2 meter per second square I hat. That should be the acceleration. This is the answer of this acceleration. All right. Now what about that forces? Forces you can find out because along to the x direction for 3 kg body, I have only t force, which is actually from equation 2 we can find out from t equal to 3a. I know the a, then I can find out equation 2 imply t should be simply 3 into a, which is going to be that 3 into 2 is going to be that 6 Newton. And from equation 1 I can write it should be 10 minus t, which is that net force acting on the block 2 kg. It should be 10 minus t is 6 equal to that 4 Newton. These are the force will be acting on this individual block. As a result, sum of these two force actually the 10 Newton. I am dragging that system with that force. All right. All right. Let's move forward. Let's say right now I am dragging, instead of dragging, I connected 4 block right now in the vertical direction. It's going to be, let's make it too small otherwise.
Sir,
Yep.
sir, do you need to calculate both vector and the magnitude of acceleration, or the magnitude only?
How do you define the vector?
So it's along the x direction, so it's vector.
No. My question is, how do you define a vector? Do you understand my question?
Yes, sir.
Then answer. How do you define a vector?
Sir, calculating the direction and
Only direction?
the value.
Yeah. So for vector, it has to be magnitude and the direction, right? So if you
Yes, sir.
only give the magnitude, that should be that scalar quantity. But by definition, acceleration is a vector. Then you have to show that magnitude and the
Okay, sir.
direction.
Okay, sir. Thank you.
Or you can write down in term of only unit vector I, j, or k, whatever the direction it has actually. I know that you are not going to show that one actually, that direction of vector, because that actually that you are not used to show that way, but it has to be in that way, because by definition vector has a magnitude and the direction. If you only give the magnitude, that's going to be the acceleration. That should be wrong. All right, keep attention over here. I have this 4 block I connected by these 4 different strings. This is A, B, C, and let's say this is the D, and this string has a different tension, because let's say the tension of this string is 9.8. Tension on this string is 49 Newton. Tension on this string is 58.8 Newton, and tension on this upper string is 98 Newton. 98 Newton. All these 4 block actually hanging from a ceiling actually. Do you understand the idea? So I just connected these 4 block by these 4 different string, which has a different tension actually. Now they asked me to find out the masses of these blocks. What is the mass of block MA? What is the mass of block B? What is the mass of block C? And what is the mass of block D as well? All right. Fine. So to solve this one, I need to draw the free body diagram. If I want to draw the free body diagram, then I need to know how many forces are acting on this individual block. Can anyone tell me how many forces actually acting on this block D?
So 2, sir.
2 force. Good. What are they?
So the tension of the string and the gravity.
Gravitational force. Absolutely, you're right. So this is actually that gravitational force, which is actually that mdg is the downward, and I should use the different color. And this would be that tension. Let's say this is actually the T. This actually that free body diagram of this object block D. Now what about the block C? How many forces over here?
Sir, still 2 forces.
2 forces. What are they?
Sir, the tension of the string below it and tension from the string above it.
Then what about the weight of this block C?
So it will be the sum actually.
Sum actually of what?
So of the tension of the string below it and the weight, that will be the sum.
No, that's not right, because this is the tension is acting because of the weight of this block D, right? It has the 3 force. One is actually, you say, the tension, which is that downward direction. Another tension is the upward direction, which is, let's say this is the T1. I use the different sign right now because previous one I used the T. And another force, weight of this block mcg. Sadman Sakib, 45 minutes late. Mr. Sadman Saqib, why are you late? All right, so do you understand right now? There will be three forces. One is the tension. These tensions arise because of this D actually that try to pull this C towards the downward because it has some weight which is mdg. That's why these T arise over here. And this is the weight of this block MC. And the same reason this T1 is arise because of it is pulling toward the downward direction. And same way you can say that this would be that T1 for the block B. This is would be MBG, the weight of the block B. Let's say this is would be my another tension over here, which is the T3, and for A it would be also MAG into T3, which is the downward, and let's say this is actually that T4, which is towards the upward. This is the free body diagram of this object. Do you understand? Is there any question over here?
No, sir.
All right, let's choose. This is my positive X and this is my positive Y. This system is not moving at all, right? Once you hanging something from the ceiling, it's not moving actually. Let's say it is stationary. It's not moving along to the vertical direction. It's not moving also along to the X direction. It is stationary right now. Then I can say the net force along to the Y axis is 0 for this system. Net force along to the X axis will be also the 0 for this system because it's not moving at all. Fine. Let's write down for block D. For block D, if I write down the net force along to the y-axis is 0, then how many forces for block D? I can see two forces. One is tension is the upward towards the positive y direction and mdg towards the negative y direction. Then I might write over here, it should be T minus mdg equal to the 0. Can I write this one?
Yes, sir.
Then T would be simply mdg, or md would be simply T divided by g, and T is 9.8, g is also 9.8. I'll find out mass of this block D would be simply that 1 kg. Do you understand?
Yes, sir.
All right. Fine. Now let's write down over here for block C, so that you can see that for block C, what I'm supposed to write? Net force again along to the y direction would be 0. How many forces for block C? 3 forces I can see. This is T1, which has a value 49 Newton. This is T, is the downward, and this is MCG is also the downward. Then I'm supposed to write it should be T1 minus T minus MCG equal to the 0. Can I write this one? Is there any question over here? Hello?
No, sir.
Sir, I have a confusion actually.
Yeah.
Sir, does here MC mean the weight of C only, or the weight of C, B, and A altogether?
No, it is actually MCG means only the weight of this block C. I am applying the Newton's second law individually for every block separately. That's why I am trying to draw it in that way.
Thank you, sir.
Alright, then MC would be simply T1 minus T divided by G, right? Then I can T1 is my 49 Newton minus T is 9.8 Newton divided by 9.8. Then I will find out MC from there. MC would be simply that it should be 4 kg. It should be 4 kg. All right. That's how actually you can solve the other two. That would be your homework. Do by yourself. Solve MD by the same procedure, MB, and also that MA by the same procedure. You have that free body diagram. Just apply the Newton second law along with the y direction. Net force along with the y direction would be 0. Then you can find out. And answer should be MB should be 1 kg. I'm giving the answer so that you can justify your answer. And MA would be again 4 kg. This would be also that 4 kg. All right. Fine. Let's move to the forward direction. Let's talk about inclined plane. Inclined plane. Right now, we have talked about only that horizontal plane. Right now, we are going to place the system in an inclined surface. Actually, that's called actually inclined plane. Let's say it's a frictionless. Again, we are considering, since we did not introduce the idea of the friction. All right, this is my plane. Let's say this plane create an angle. This is theta. This makes an angle with the horizontal surface. I keep a block over here which has a mass is m. If I keep the block over here, what it will going to do?
So if the surface is frictionless, it will move downwards, but like along the surface.
Along the surface, exactly. You're right. So if I ask you why it is moving to the downward direction?
So acceleration due to gravity.
Acceleration due to gravity. All right, that's good. So that means the gravitational force is not a gravitational force. The component of the gravitational force actually doing that job, because I know that this is to be my gravitational force, right? Is the mg. And how many force would be over here on the block?
So 3, sir.
What are they?
So 3 forces.
What are they?
So the weight, the
Mhm.
component of the weight, and the reaction force.
Yeah.
Normal reaction force.
Normal reaction force. This should be 2 force actually, namely 2 force. This is actually that normal reaction force. The component of force would be, when you consider the component of the force, then this resultant force would be omitted from there actually. Right. This is actually the namely 2 force is acting on that system, but we will split this one because if you say that this block is moving for the gravitational force, then technically it should be wrong, because then this block is supposed to be moved to the downward direction because that force is downward. All right. According to the Newton's second law, it is supposed to be moved in the direction of your net force, but it is actually moving towards that direction. It means that there might be some component of that force that we are going to find out. We need to find out that one. That which you say that the component of that gravitational force will do that job to drag the block towards the downward. All right, so I need to find out that one. So if it is theta, then what is this angle? This angle is 90, right? What should be this angle?
90 degree minus 3.
90 degree minus theta. Then this component should be mg cos of 90 degree minus theta. Am I right? Which sometime we directly will be write mg sin theta. And this would be one more component, because that angle will be theta over here. because this angle is 90 degree. Although my drawing is not exact, but this should be 90 degree, remember. Obviously, it should be 90 degree. This angle has to be 90 degree. Then this component would be mg cosine theta. Now, if you write the, let's choose this is my positive x direction downward, and this is my positive y direction. If I write net force along the y direction would be 0. Can I write this one? Why I am writing? Because the block is not moving in the y direction. It is moving towards the x direction only. So that's why I am writing net force along the y axis would be 0. Then I am supposed to write it should be n minus mg cos theta equal to the 0. I am sorry. Then n should be mg cos theta, right? Which is actually, it's the apparent weight of this block again, because your actual weight should be the mg. Right now it is different from mg, so that's why it's called the apparent weight of the block. Now what about along the x direction? I can see from this free body diagram I have only one force, which is the mg sine theta along to the x direction. Then I am going to write it should be mg sine theta must be equal to ma, or this m will be cancelled out. You can write a should be simply g sine theta. I should write proper way so that otherwise a would be simply that g sine theta. That's how actually it should be the acceleration of the block.
Sir, why won't the G and A cancel out? Aren't both of them? Oh, aren't both of them the same value?
I didn't get you. Which one? Can you tell me again?
I'm saying that why aren't we canceling G and A, because they're of the same value?
Is they are in the same direction?
No.
Then it about the vector, guys.
Oh. Oh.
Right.
My bad.
Yeah, that's fine. Yeah, here is my ST right now. CR7, where you are?
Sir, I had network issues. That's why I couldn't join.
Come on, you should be more responsible. All right, you missed a lot of things actually. Very important class we are doing. All right, so is that okay?
Yes, sir.
All right, so that's how actually we can find out this acceleration in inclined plane. Right now, if I know that acceleration, then I'll be able to find out how much distance will be traveled this block, or what should be the speed of the block after traveling some distance, because that we know that from our previous chapter, which is the motion in the 1D or the 2D, right? Because once it moves at acceleration a, which is the g sine theta, then you are able to treat that system because it is moving at a constant acceleration, right? If you release that block, obviously it will move at a constant acceleration over here, right? Do you understand? Because this one will move at a acceleration g sine theta. Sorry, it's a g sine theta. A should be simply the g sine theta. Now look at this, it is interesting. So if I have, let's say I have two identical inclined plane which has a same angle, also the same material. Now what I'm going to do, I'm going to release two block. One is a mass m, another is, this is also the identical plane over here, and in another case I have a bigger m, different mass actually. Let's say this capital M is greater than actually that bigger M. Now if I release that two systems at the same time from the same height, let's say from the same height, now which block will we come down first? Can anyone tell me? If I release these two
So
systems,
they'll fall at the same time.
they'll fall at the same time. Is there any other answer rather than this?
So they will fall at the same time, I guess, according to Galileo's law.
According to Galileo's law?
So if I'm not wrong, like if a feather and like a metallic ball is like they'll let fall freely and there's no air friction, they will fall at the same time.
Yeah, but this one is I'm not doing in a free space actually. I'm doing, let's say, in a normal. Only I'm saying that system has no friction actually over here. Yeah, your answer is right. Absolutely, you are right. They will obviously fall at the same time. That the reason is obviously over here. It's simply that acceleration is the z sine theta. It is independent of the mass, right? This
Yes, sir.
acceleration is independent of the mass. It's depend only on the angle theta and also the z. Since we are doing the same experiment in the same place with the same identical inclined plane, so they will move with the same constant acceleration, and that acceleration is independent of the mass. That's why they will come down at the same time over here, which means the match will be tie over here. But if it is a frictional, then this system is going to be different, right? That depend on actually the coefficient of kinetic friction between the block and the inclined surface actually. All right. All right. Let's talk about. I have a block over here which has a mass actually that m, and I'm going to drag this block with applied a force F, making an angle is theta. Now they give some value of this system. F is 15 Newton, m is 3 kg, and the angle theta is 38 degree. Now they asked me to find out what is that number. Question 1 is what is the acceleration of the block. Second one, what is the apparent weight. I'm writing that keyword, apparent weight of the block. Number 3, this is interesting, what is the F minimum force, F minimum required for the block, to lift off from the surface. It means that, let's say I am applying the 15 Newton, probably due to that 15 Newton actually the block is traveling towards this x direction. But let's say if I apply the 100 Newton in that direction, instead of moving in x direction, it will move into that direction, in the direction of the force, right? It could be 50 Newton, it could be obviously it could be 70 Newton sometime. But I don't want that forces. I want to know actually what is the minimum force is required just to lift up from the surface. That's what I'm saying. That we'll do that later. First, do that first too. Let's draw the free body diagram. If I draw this free body diagram, oh God, sorry. I do not like these online classes. This is actually that mg. This is my normal reaction force. This is the force component actually that F cos theta. This is actually that F sine theta, right? Am I right? Did I draw the free body diagram properly? Do you understand that one?
Yes, sir.
Right. To solve the first one, I can write this force along to the x direction. It should be that ma. If you look at this free body diagram, I have only one force towards the x direction, which is the F cosine theta. Then I am supposed to write, it should be, this is solution I am supposed to write. So F cos theta should be equal to ma. Then it implies me A should be simply F cos theta divided by m. I know this value. F is 15, cos angle is 38 degree, divided by mass is 3. Then you will find out this A is going to be that 3.94 meter per second square. And it's a vector, you have to give that direction. Then I am supposed to write answer should be vector 3.94 meter per second square I hat, because this block will move at an acceleration towards the x direction. Right, that's why.
Sir, I have a question.
Sure.
Sir, while mentioning the vector acceleration, should I also mention the unit, or just putting I cap there is enough?
It's a standard way to actually express in terms of unit actually. So it's a good practice actually to show that, mention the unit of this system when you're dealing with that physics stuff actually.
Thank you.
But a vector has to be properly addressed, otherwise I will deduct your marks in the mid, quiz or the final. Alright, this is actually that acceleration. Now to find out the apparent weight, I'll write second part actually, the net force along to the y-axis would be 0. If you look at this free body diagram, there are 3 forces along the y direction. 2 is towards the positive y direction, which is n and f sine theta, and mg actually towards the negative y direction. Then I am supposed to write this equation. It should be n plus f sine theta minus mg equal to the 0. Then I can write this n should be simply mg minus f sine theta. If you plug in those value, you will find out this one is going to be that it should be simply 20.17 Newton. That should be the apparent weight of this block. Alright. Now the question number 3. This is important. Try to understand this one. They asked me what should be that F minimum so that this block, instead of moving towards the x direction, it will be fly off from the surface in that direction. We are going to find out. Let's say if anything is going to be the fly off from the surface, if this block is going to be the fly off from the surface, what would be the change? The change would be the normal reaction force is going to be that 0 in that case. Remember, anything going to be the lift out from the surface, the normal reaction force on the surface must be going to be equal to the 0. This is a very important point. If anything is going to be that lift out from the surface, there will be no normal reaction force will be acting on the system. Why? Let's say if this block is no longer connected to the surface, then who will be provide this normal reaction force on this block? Right? There will be no contact to the surface, there will be no normal reaction force. That's why the normal reaction force must be going to be the 0. If anything is going to be the lifter from the surface. The best example I can say you another way actually. Let's say when a airplane actually take off from the surface, this normal reaction force of this aeroplane is going to be the 0. How it's become 0? Let's say this is when it is actually on the runway. In that case, how many force it has? It has 2 force. One is actually that weight of this force, weight of this aeroplane is a downward. Another actually that normal reaction force, right, by the Newton third law, although this force would be acting on this two wheel of this aeroplane actually. And when it is in the runway, these two forces are equal, right? That's why it's not moving along the vertical direction when it is actually the stationary case. Now, if it is, how does the airplane actually take off from the surface? Because this N is a huge weight. This is the innermost weight of this plane it has, right? Normal reaction force is very high over here because that weight is also, this plane is to be very high. Then how does this take off this from this surface, or how does it going to be minimize this normal reaction force? Because I say that if it is want to take off from the surface, obviously this normal force is going to be 0. What happened actually, this airplane actually run with a very high acceleration in the runway to minimize that normal reaction force. How? That's actually the Bernoulli's equation. Very interesting equation. One of my favorite equation is also, it has a lot of application. I'm going to tell you, it will be very interesting. When this actually move with a very high speed toward the forward direction, a up thrust is going to be gradually increased. How does it increase? If you ever closely observe, the wings of the plane is look like that, right? If you observe it very closely, you will see that the wings of the plane is look like that one. That's the aerodynamic design actually. Why they do that actually? When that actually air molecule run in that upper surface instead of this down surface, this upper surface molecule has to be covered larger distance with respect to the lower surface. That's why they move at a very high speed with respect to the lower molecule or the surface. It means that higher molecule, upper molecule has a higher speed, lower molecule has a lower speed. If the speed is high, then the pressure will be low. If the speed is low, then the pressure will be high, which is actually the Bernoulli's equation. It says that P plus is a pressure head is called that half of rho V square actually that constant. This is the simplification of the Bernoulli's equation. This is very interesting equation. You use that equation in every day. You use that equation. I'll say that. According to this equation, if that velocity is high, then the pressure should be the low, right? To make that total system is constant. If the velocity is going to be increased, then the pressure should be decreased to make it constant. That's why when this actually run with a very high speed, the upper surface molecule, then the pressure will be low with respect to the lower surface, and the pressure is always move from high to the low, right? Pressure is fall from always high to low actually. That's why a net pressure or up thrust is going to be created over here. When the plane actually run with a very high speed, gradually is going to be increase this up thrust. Once it's equal to that weight of the plane, then it's in the balance, which is on the verge of the fly of this plane actually. Right now, the net force along the y-axis is 0. Then after, if you increase that velocity, this one is going to be the increase. Right now, you have a net force towards the upward direction. This is one force, this is another force in that direction. You have that resultant force actually, this one. That's why the plane take off in that way. This is the application of the Bernoulli's equation, which means this normal reaction force is going to be 0 over here. There are a lot of other interesting application of this Bernoulli's equation. Let's say one case actually. So you already observed that one. Do you know actually when in a cricket, in a fast bowler actually, when they're going to swing the ball, they make a rough one side of that ball. Do you know why they do that? Does any of you know over here why they make the rough in one side of the ball?
For friction.
Sir, for swing,
For
in swing or out swing.
Yeah, what is the mechanism? Mechanism is simply this Bernoulli's equation. Look at this, I'm telling you, it's very interesting. When they make a rough in one side, what happen on the other side is sinusoid. So if that side is rough, then it will be create a friction with the air with respect to that surface. If the friction is high over here, then the velocity will be low, right? If the velocity is low, then the pressure will be high over here with respect to that surface. That means when you make a rough in one side, in that side there will be air friction between that rough surface and the air molecule. Due to that friction, there will be velocity lower in that side. If the velocity is low, then the pressure will be high. If the pressure is high with respect to that one, then the ball is going to be actually that swing in that way, because pressure is high with that side. That's called actually in swinger, right? They use that way. And for that out swinger, they keep the rough surface in that side, this side. This is the rough, velocity is low over here. If the velocity is low, then the pressure will be high and the ball will swing in that way. This is out swinger. And for the reverse swing, they make a both side rough actually. There is one more application I can say you, another application. That is also the Bernoulli's equation. If you closely observe of a racing car, at the back side of the racing car, there is an extra thing they use in that way, right? Did you ever notice that one? The back side of that car they use in that type of shape. Why they do that? Because it's the same reason. This is the air molecule passing over here. In that case, this is covering the larger distance, which means the velocity is high. If the velocity is high, then the pressure is low.
So what did you write on that equation?
Racing cars actually.
What did you write over there? P is down plus PV square
No.
half
So no. This
equals
is the
to
constant. Equation is P plus half of rho V square equal to the constant. That's called the Bernoulli's equation. P for pressure is said in another way. This is called actually pressure head. This is called actually the velocity head. This is used for the fluid system actually. Air is also a fluid actually. Right. Then actually what happened for this case, this is a velocity is high, then the pressure will be low, and this one has a velocity is low, then the pressure will be high, and it will keep that down thrust pressure on that car, so that the car is not giving that bumping on the road actually. To keep the car on the track, they design in that way. There is one more application which every day you are use. That's called the atomizer. We say the atomizer in the physics, which is simply you use your body spray. That's also the application of the Bernoulli's equation. This is called actually atomizer in physics actually. We say once you create a pressure over here, then the velocity is high over there. If the velocity is high, then the pressure is low with respect to that surface. In that surface, if the pressure is high, that one is going to be that climb up, and that actually is spray in your body. That's called also the atomizer. We say the atomizer in physics. That is also application of the Bernoulli's equation. There are a lot of interesting application of this equation. So that's why it's very useful equation in the fluid dynamic system. We talk about that course in our fluid mechanics actually. All right, come to our point actually. Remember, that's what actually I'm going to tell you. If anything is going to be the lifted from the surface, your normal reaction force must be going to the zero, right? That was the part over here to saying that one. I described those part. So let's say if it is going to be the zero, then I'm supposed to write this is my mg, this is my normal reaction force, this is my f cos theta, this would be my f sin theta, because this was my f, which makes the angle over here. I'm going to write down this one should be net force along the y direction will be equal to 0. Then I'm supposed to write this is the stationary case, n plus f sin theta minus mg equal to the 0. If it is want to lift from the surface, then this n is going to be the 0. Then it should be that f minimum actually over here. then I'm supposed to write this F minimum is going to be simply mg divided by sine theta, and if you solve this one, you will get that this F minimum should be 47.74 Newton. That should be the F minimum force should be required. It should be, that is actually that force, which is in that case it will be on the bars of the movement. If your force is 57.8 Newton, obviously it will be fly off from the surface. That's called the F minimum requirement force. Or you can say another way, that is the maximum amount of force you can apply to drag the block towards the x direction. That is the maximum amount of force which is required to move the block along to the x direction. If it is greater than 47.74 Newton, then instead of moving towards the x direction, this block will be fly off in the direction of your block, which means that it will be no longer connected to the surface. Remember this one, to fly off a surface, obviously that normal reaction force must be equal to the 0.
Sir, can you go a bit upwards?
Yes, why not?
I did not finish copy.
I said you don't have to take this note, actually I will give you this handout.
So if the block gets up from the ground, sir, it doesn't have any apparent weight, sir, right, sir?
I didn't get you. Say it again. What do you say?
If the block gets lifted, then it will have no apparent weight, right,
Yes,
sir?
yes. Is it finished? Can I move forward?
Yes, sir. Yes, sir. You can move forward.
Thank you. Where is my seer? Seer, are you there?
Yes, sir, I am.
All right. I thought again you left because of a network issue. We have one more class in tomorrow, right?
Yes, sir.
All right. Oh, today is 29th February. Oh my God, it's a leap year. All right, so this is another case. Actually, you have this theta inclined plane. I keep this solid sphere. Somehow I make this, keep it stationary over here, connected by this string. This give us some information. The mass of this solid sphere actually that 5 kg. That theta is 35 degree. They ask me to calculate the tension in the string. Second one is what is that normal reaction force on the ball provided by the surface. How many force will be acting over here?
So 4 forces.
What are they?
4 or 5. So the weight, the what do you call it? Apparent weight, and the tension,
3.
and sir, the mg sin theta and cos theta.
Oh, that's the component of this your mg. It's not a different force, right? It's not a different force.
So 3 then, sir.
3 force over here. This is would be your mg. This is normal reaction force. Look at this normal reaction force. I'm drawing in perpendicular to that inclined plane, not in that direction. It has to be perpendicular on that surface. These are the 3 forces, and there is a tension over here. This is the tension. This is the 3 force actually acting on that. Let's split these forces. Actually, I have to do that one because I'm going to choose. This is my positive x direction, and this is my positive y direction. I need to split that one. This is angle 90. This is would be 90 degree minus theta. then this component, this angle would be theta, this would be one component, this would be mg cos theta, this should be this, because this angle is 90 degree minus theta, it should be mg cos of 90 degree minus theta, it will be automatically give me mg sin theta. Am I right? Do you understand this free body diagram?
Yes, sir.
Come on guys, try to understand. Step by step we are moving to the more complex system. If you do not understand this free body diagram, then it will be difficult for you to solve the problem. Alright, so I split that forces, this m towards my x and y direction. Now I have to also split this t over here, because this t is not towards my x and y direction, right? Can you tell me what should be this angle? It should be theta, am I right? It should be theta, because look at this, if you have two parallel line and if you have an intersect, these are the angle, actually alternative angle, because my that line, let's use the different color so that you can understand. I'm going to use which color? This one.
Sir, alternate angles.
Yes.
Thank you, sir.
No, this is not. I should use this one. Green color, yeah. Alright, so then I'll find out, this would be my one component of the t, and that should be another component of the t. If this is theta, then what? This would be also the theta. Again, this line and this line and parallel, so that should be alternative angle. That's why this would be t cos theta, and downward component should be t sin theta. You understand this free body diagram? Alright, so if you do not respond, I would thought that you are okay with that one. Alright, so right now I'm looking to find out that tension in the string, then I'm supposed to write down the net force along to the x direction is 0. Now, this is my reference axis right now. I'm using this reference axis, because that solid sphere is not moving along to the x direction and along to the y direction. It keeps that stationary by the string, so that's why the net force along the x direction and the y direction would be 0. If I write down the net force along the x direction 0, then it should be t cos theta minus mg sin theta equal to the 0, because these are the two forces. One is the t cosine theta towards my positive x direction, and t sin mg sin theta is towards the negative x direction. So that's why I give the minus sign over here. Then I can find out this t from there. It's simply that linear algebra. It should be mg tan theta sin theta divided by cosine theta. Then you will find out, if you plug in m is 5 kg, g is 9.8 and theta is 35, then you will find out this tension is would be 34.3 Newton. That should be that tension in the string. This is the answer of the first question. Now for along to the y direction, you can write the net force along to the y direction is 0. Then you are supposed to write it should be n minus mg cos theta minus t sin theta equal to the 0, because I have n towards the positive y direction, t sin theta is towards the negative y direction, and mg cosine theta is also towards the negative y direction. So that's why these two quantity would be negative over here. then you can write this, you can find out this n should be from there, it should be mg cos theta plus t sin theta. That should be that normal reaction force, and if you plug in those value, you will find out this normal reaction force would be 59.78 Newton. This is again the apparent weight of this solid sphere, because it is different from this actual weight. Actual weight is simply that mg. Right now it is different from that one, so that's why it should be again that apparent weight. Alright, can I get 10 minutes extra? Hello?
Yes, sir.
Sir, yes, sir. Sure.
Thank you. Alright, let's say this is the inclined plane again. This makes the angle the theta. In that inclined plane, you are dragging, sorry, it's very disturbing. You're dragging this block, applying some force actually. The mass of the block is m, is given, and you are dragging, due to that, dragging this one at acceleration a towards the upward direction. They give us the mass of this block is a huge weight, 150 kg, and that angle is 20 degree, and due to that applied force, that block is moving at a 2 meter per second square towards the upward direction. Now the question they ask you, how much force should you apply to drag this block with that acceleration? It's very simple. You can draw that free body. It's wrong. This is that mg. This is my normal reaction force. This would be my mg cos theta. This would be my mg sin theta, and this would be my applied force applied by u actually over here. Let's choose this is my positive x direction, and this is my positive y direction. Now I am concerned only about that forces which is acting on the towards the x direction. So that's why I'll write the net force along to the x direction would be equal to ma ax. I'm not concerned about the vertical direction because they don't ask me to find out the apparent weight. So that's why I'm not concerned about that part. How many forces along to the x direction? Right now I have the two force. One is F, which is towards the positive x direction, and another actually that mg sin theta, which is towards the negative x direction. Then I'm supposed to write it should be F minus mg sin theta equal to that ma. I'm going to find out that F from there, it should be simply ma plus mg sin theta. You know the everything, you know the mass, or you can factor out this one. M, if you factor out the m, it should be a plus g sin theta, right? So then you can find out this force should be, F should be 802.76 Newton. It's a huge force you have to apply if you want to drag a block which has a 150 kg mass in an inclined plane which makes the angle 20 degree at the acceleration 2 meter per second square. Then you have to apply that amount of force, which is 102.76 Newton actually. What will happen, let's say if I include the friction into the system, in that case will I have to apply more force or less less force of this one?
So more force.
Force. All right. Is there any other answer? Is someone telling me? This will be less force of this. We'll see that when I'm going to talk about actually that frictional case. We'll see that in that case that force will be less than this. Let's talk about that pulley system. It's very disturbing.
Sir,
Yeah.
sir, when are you taking our attendance?
Which one is important? Attendance is important or topic is important?
The topic is important.
Yeah.
The topic is important.
Then why are you asking for that attendance? Pay attention on the topics. Attendance is not a big deal. I'll give you your attendance, don't worry about that. Alright, so let's say I have this is a two pulley, it's a massless and frictionless pulley we are using over here, remember. If it has a mass and it has a friction, then the system is going to be the different actually, which should be more complicated. We are not going to make the complicated thing for you at this level or this Newtonian mechanism. We make this, we consider this part when we actually talk about the classical mechanics for the physics major student actually. Alright, so let's say I connected two mass over this pulley by this string. One is mass M1 and this is that mass M2. Let's say I'm considering M1 is greater than M2. What will happen in that case? General idea is that if M1 is greater than M2, then this M1 will move to the downward direction, right? And this M2 will move to the upward direction with the same acceleration. Am I right?
Yes, sir.
So I want to find out that acceleration from here actually. What should be that acceleration? To find out that one, I need to draw the free body diagram. How many forces will be acting for this M1 over here? It will be two forces. One is M1G towards the downward, another force actually the tension in the string, which is the T, is the upward direction. What about for M2? It has also the two force. One is M2G is the downward, and this will be the also the T is the upward direction. Now look at this. I use the same symbol for this tension because it is the same string. That's why the tension are same. Alright, so now we're going to find out that this acceleration, I'll write down the Newton's second law actually. That now this time I'll do it at a time. I'll simply write down net force on each of this block should be that MA. I'm going to write down simply the magnitude. For block M1, I can write, since this M1 is moving to downward, then M1G must be greater than T. It has to be. Right. Then I am supposed to write net force would be M1G minus T equal to M1A. Can you write this one for block M1? Please try to understand. This is very important part, one more case. Can you write this one?
Yes, sir.
Yes, sir.
And for block M2, it should be T minus M2G equal to M2A. Why? When this M1 is moving to the downward, then M1G must be greater than T. Otherwise, net force is not going to be towards the downward. If M1G is less than T, then the net force should be towards the upward direction because T is bigger than M2G in that case. Then it might supposed to move towards the upward direction. Since I assume that m1 is moving to the downward. In that case, m1g should be greater than t. We have that Newton's second law to make this consistent with that Newton's second law, because Newton's second law tells us that the system will be moved in the direction of the net force. If m1 moves to the downward direction, it means that the net force is downward. Net force is downward means the downward force must be greater than upward force. The same reason, if m1 moves to the downward direction, m2 will move to the upward direction. In that case, t must be greater than m2g. So that's why I write down this format over here. Then I'm going to add them together. If I add, this t will be cancelled out. Then I'll find out m1g minus m2g equal to m1a plus m2a. I can factor out g and m from both two sides. If you factor out g, it should be m1 minus m2.
So can you go a bit upward?
Sorry, I didn't get you.
Can you go a bit upward? I'm copying.
Oh, sure, why not?
Yeah, here. Thank you, sir.
Alright, then I can find out the acceleration from here. It should be simply m1 minus m2 into g divided by m1 plus m2. That should be the acceleration of this system. Don't try to memorize this equation, because this equation format will be the change. Try to understand the procedure actually I am doing over here. I am simply writing the Newton's second law for individual system or individual block, individual case. Then I am adding these two equations to find out my requirement, which is actually the acceleration over here. That's how actually you will be able to find out this part. Oh, it's a 9:42. I don't want to do one more problem. I have one more problem actually to solve this chapter. Then I'll move to the next chapter. I'll do this in the next class actually. Or should I finish it right now?
No, sir. No, sir. I have to
So
go out.
next class.
No, sir.
Alright, so thank you very much guys for your support. And should I take the attendance?
Yes, sir.
Yes, sir.
Yeah, CR, you are
Yes,
late.
sir. Sir, we earned it, sir.
Yeah, don't be late in the tomorrow. Tomorrow we have also one more classes from 8:30. Not
Yes,
the
sir.
8:30, at 8. Sorry, not at the 8.
8 p.m.
8 p.m. Yes, exactly. All right, so do one thing actually. Write your name and the ID in the chat box. Do it. Hurry up. But that attendance is too low actually. Only 23 guys is over here present. You're supposed to be present over here. Remember, this is the very important topics I talked today. And you will definitely get one question from these topics, from Newton's law with and without friction. I'm going to set up a question for the meet. And we have also quiz in the next Tuesday, right? CR7, didn't I announce a quiz in your class for one more quiz?
The quiz will be
Yes, sir.
Wednesday, you said.
Oh, Wednesday, yes, obviously. We don't have any class Tuesday with you guys.
No, sir. Not Tuesday, Wednesday.
It should be Wednesday, yeah. And what was the topics? It should be Newton's law, right? The topic should be only the Newton's law without friction. I am not going to include the friction in that case. Only the topics I talked today actually. This would be your third quiz topics. Alright?
Just the Newton's law? Or do we
Just the
have to
Newton's
read,
law,
what-
yeah. Rohan is trying to add right now. Rafsan, Jani, Rohan.
Yes, sir. Present, sir.
Yeah, are you present in the whole class, or right now you just
Yes,
come
sir.
to
I
give
was
the?
there. No, sir. I was present the whole class, but I got disconnected few minutes ago.
All right, so fine. So did you give your attendance?
Sir, no, sir. I couldn't give the attendance. I joined right now. Thank you, sir.
All right, give your attendance in that case. All right, guys. Thank you very much. If you do not have any question, you can leave. We'll meet in tomorrow again. Thank you very much.
Assalamu alaikum.
Wassalam.